First tricky example, or the first maybe interesting example of a differential equation, which I'll call example 2, is going to be the following. D by dx plus x acting on y is equal to 0. So that's our first differential equation that we're going to try to solve, apart from this standard antiderivative approach. This operation here has a name. This actually has a name. It's called the annihilation operator. And it's called that in quantum mechanics. And there's a corresponding creation operator where you change the sign from plus to minus. And this is one of the simplest differential equations. The reason why it's studied in quantum mechanics at all is that it has very simple solutions that you can just write out. So we're going to solve this equation. It's the one that governs the ground state of the harmonic oscillator. All right? So it has a lot of fancy words associated with it, but it's a fairly simple differential equation, and it works perfectly by the method that we're going to propose. So the first step in the solution is just to rewrite the equation by putting one of the terms on the right-hand side. So this is dy dx is equal to minus x times y. Now here is where you see the difference between this type of equation and the previous type. In the previous equation, we just had a function of x on the right-hand side, but here the rate of change depends on both x and y. So it's not clear at all that we can solve this kind of equation. But there is a remarkable trick which works very well in this case, which is to use multiplication, to use this idea of differentials that we talked about last time. Namely, we divide by y and multiply by dx. So now we've separated the equation. We've separated out the differentials. And what's going to be important for us is that the left-hand side is expressed solely in terms of y, and the right-hand side is expressed solely in terms of x. And we'll go through this in careful detail. So now the idea is, if you've set up the equation in terms of differentials as opposed to ratios of differentials or rates of change, now I can use Leibniz's notation and integrate these differentials, take their antiderivatives. And we know what each of these is. Namely, the left-hand side is just, well, that's tough. Okay. Yeah, I had an au pair who actually did a lot of taekwondo, and in fact, she could definitely defeat any of you in any encounter. I promise you. Okay. Anyway, so let's go back. We want to take the antiderivative of this. So remember, this is the antiderivative. This is the function whose derivative is 1 over y. And now there's a slight novelty here. Here we're differentiating the variable as x, and here we're differentiating the variable as y. So the antiderivative here is natural log of y, and the antiderivative on the other side is minus x squared over 2, and they differ by a constant. So we have this relationship here. All right, now that's almost the end of the story. We have to exponentiate to express y in terms of x. So e to the log y is equal to e to the minus x squared over 2 plus c. And now I can rewrite that as y is equal to, I'll write it as a e to the minus x squared over 2, where a is equal to e to the c. And incidentally, we're just taking the case y positive here. We'll talk about what happens when y is negative in a few minutes. All right, so here's the answer to the question almost, except for this fact that I picked out y positive. Really, the solution is y is equal to any multiple of e to the minus x squared over 2, any constant a positive, negative, or 0. Any constant will do. And we should double check that to make sure. If you take d by dx of y, right, that's going to be so that's going to be a times d by dx of e to the minus x squared over 2. And now by the chain rule, you can see that this is a times the factor minus x. That's the derivative of the exponent with respect to x times the exponential. And now you just rearrange that. That's minus x times y. All right, so it does check. These are solutions to the equation. The a didn't matter. It didn't matter whether it was positive or negative. Now, this function is known as the normal distribution, so it fits beautifully with a lot of probability and a probabilistic interpretation of quantum mechanics. This is sort of where the particle is.